Ali Jan Bey. What you see here is the turbine spinning around now. The water flows through it. Water comes from the sea into the channel. On top of it, on a vertical axis, you see a big green generator, and that makes the energy from the water to electricity.
Fantastic. Here in the Netherlands, tides aren't just for recreational surfers. They're also used to power the country. By capturing the ocean's ebb and flow, the Dutch are also turning it into a renewable power plant. Humans have always looked to water with both reverence and hunger. Ancient myths speak of sea gods and tides that could make or break civilizations. Folklore from island nations warn of floods. Coastal legends praise the calm at dawn. Even centuries ago, dams and water wheels tried to tame currents in rivers. In modern times, most of the harnessing has been river-oriented. Hydropower in valleys, dams in mountain gorges. The sea was something else entirely. Wild, unpredictable, untamable. But now, science and engineering are catching up. Two schools of ocean power are coming together. Kinetic energy, the push and pull of waves, tides, and currents, and chemical or osmotic methods, utilizing the gradients between fresh and salt water. The ocean is both motion and chemistry, a reservoir of fuel and force. Unlike wind that dies in calm weather or solar that sleeps at night, blue energy promises something more consistent. Tides never rest and salinity differences never fully vanish. The sea moves and moves again almost forever. And now we're learning to turn that motion into electricity. The Netherlands has long been a leader when it comes to renewable energy, and the offshore wind farm behind me is proof of that. By placing turbines at sea, the Dutch make efficient use of space in a place where land is scarce. For the Netherlands, water isn't just a challenge to overcome, it's also a valuable source of energy. One of those innovations rising from these waters is RedStack. They specialize in membrane stacks that generate power by mixing fresh water with seawater. A chemical dance you don't really see, but one that pushes electrons. Their installations are often placed on or alongside dams and dikes, where fresh waters meet their saltier cousin. Needless to say, you can't find a more ideal spot than the Netherlands. Pumps draw the water, membranes let ions flow, generating blue energy continuously. No solar gaps, no waiting for storms. And that constant potential is what Peter Hack, RedStack's founder, has been pushing toward, with his eyes always on both power and permanence.
Well, preferably the seawater is very salty and a bit warmer. So around the Mediterranean, there would be the better places to be, where the rivers empty into the sea, or looking at other applications, which would the brine, the concentrate of a seawater desalination plant, where they produce tap water out of seawater. They have a waste flow, the brine, which goes back into the sea normally. And parallel to that, many times there is a wastewater treatment plant treating the municipal wastewater, nice, the treatment, discharge into the sea, which is a fresh water.
Okay, so that's the intake for the fresh water.
Yep.
And that follows this black pipe over here. And just a little further down, this is where the two different types of water, they come in and go into your filtration system and into your plant.
Yeah. So before we can harvest energy, we first have to filter the algae, the larvae and so on. We have to filter out the sand, has to be out, because we don't want to get the membranes to get clogged. but you do that very careful to make sure that we don't kill any algae or whatever, and guide it back into the seaside. And then after it has been filtered here, we go inside where the membrane stacks are there, and that's the machine where the equipment, where the power is being generated.
Because this is a environmentally protected zone, you're mandated to actually protect all of the marine life that you take in from the salt water.
Yep.
And then you actually discharge the salt water back into the ocean as well.
Yeah, the concentrated flora fauna we gently guide back, so we don't kill anything. We just keep it as it is. And the fresh water we're using, we don't consume it, we only borrow it for half a minute to extract the energy. So we're last in line for using the fresh water before it's being discharged into the sea anyhow.
At the meeting point of the river and sea, a hidden power source flows. This difference in salinity is what drives blue energy. Before energy can be extracted, both fresh and salt water are carefully filtered. The water is carried along these massive pipes to ensure clean flows into the blue energy power plant. Inside the plant, stacks of specialized membranes form the heart of the system. These ultra-thin layers allow ions to move from salt water into fresh water, and that movement is what creates electricity. Fresh and salt water flow in through 4 pipes, 2 bringing in, 2 carrying out. The streams are carefully controlled to maximize the ion exchange process. RedStack's system funnels fresh and salt water through alternating ion exchange membranes. Salt ions pass through in opposite directions, generating tiny voltages across each pair. Electrodes capture this charge, converting it into electricity. Stacked together, thousands of pairs deliver continuous, zero-emissions power right where the rivers meet the sea. We went inside RedStack's pilot plant, where Peter shows us the guts of the operation and how the membranes are arranged like pages in a book, stacked in modules.
We have 2 membranes, 2 different types of membranes. One membrane where the positive part of the salt can pass through, the sodium and others. Another membrane where the negative part of the salt, the chloride and others, can pass through. And we stack them as flat membranes alternately. A plus, a minus selective membrane. And then we guide the water, the salt water and the fresh water, in parallel between the membranes. And the salt from the salt water wants to move to the freshwater side. But because of the selective membranes, the positive only can go in one direction from the salt to the fresh. The negatives have to go in the other, opposite direction from the salt to the fresh. So you create 50 millivolts of tension on every membrane. But when you have 1,000 membranes in parallel, you create 50 volt DC, which you harvest at the end. And then the water, the salt water, fresh water is pre-mixed, and it could leave the stack as kind of a brackish water to continue its flow into the sea. And from technological point of view, it's the same thing here. The flat membranes are in it. The fresh water, the salt water comes in, the mixed water comes out, and the power we harvest here. And this construction is only to keep it in mechanical shape. And then we start to do engineering. We left process technology, go into mechanical engineering to make it more efficient from construction point of view. The same membranes, same square membranes are inside. Between the tube and the membranes, the water is distributed from front to back, from left to right, that each and every membranes get the same amount of water, very homogeneous flow distribution, and we're harvesting the power here.
What if the same power plant that lights up your home could also help decarbonize the planet? Well, that's the idea behind the next wave of innovation, where the lines between energy production and climate repair start to blur. RedStack is a pioneer when it comes to blue energy technology, and at its core are its super efficient membrane stacks. Besides being used for creating energy, it can also be used for desalination, extracting ammonia from waste flow, and capturing carbon from liquids. And from liquids, I mean the sea. And there's one company that's doing just that. Meet SeaO₂. Their mission? Draw carbon straight from the seawater. They harness the chemical potential of the sea. Using electrochemical stacks, they shift pH, release CO2, and capture it. In essence, turning the ocean not just into motion, but into cleanup crews for our carbon overload. It's delicate chemistry and engineering. Fresh meets salt. Electrodes and membranes do the work. Renewable energy powers the cycle. And standing at the helm of that mission is Martin Uthorn. And he's going to show us their system in action.
After taking in the water, we have a series of pre-filters, sand filtration to, in small steps, going from large to small, remove all of the unwanted components. The filtration process starts at the intake of seawater, where we have a special filter to make sure that we don't take in any fish or mussels or all sorts of bigger sea life. And in multiple steps we go down all the way down to atomic level to remove these specific atoms that we really can't have in our process.
The balance between alkaline and acidity plays a key role in this whole process, doesn't it?
Absolutely. Chemical reaction of water and carbon dioxide is driven by the acidity. So if you're alkaline, the equilibrium is on the carbonate, which is the product of water and carbon dioxide. If you acidify, you switch that equilibrium all the way to the gaseous CO2 side. So what we do here is, after taking in the seawater and the series of filtration steps, we go right here to the heart of our process. In the heart of our process, we use electricity to split water in an acid and a base. That only works if the salt is there, because the acid is hydrogen chloride, so you need the chloride from the salt, and the base is sodium hydroxide, and the sodium comes from again also the counterpart of the chlorine in the salt. After the removal of the carbon dioxide, we actually put the base back, and this is crucial to restore the carbon dioxide removal capacity of the ocean. If we wouldn't put back the alkaline, we would just be acidifying the ocean, actually making the planet worse, not better.
I also caught up with Rubens Branda, the founder of SeaO₂. He walked me through the early days, prototypes, failures, and breakthroughs, all of which shaped a blueprint for this technology.
So we work with the ocean as a big ally to fight climate change, right? And 71% of the Earth is ocean. 33% of all the emissions end up in our oceans. And here is what it is. In 1 liter of water, there's 150 times more carbon density than in 1 liter of air. So we say it's much more energy efficient to work with that water, because when I extract 1 ton of CO2 out of the ocean, it extracts 1 ton of CO2 out of the atmosphere, again into the ocean. It's called Henry's Law, and we're making use of that.
For somebody who hasn't heard of DOC, direct ocean capture, how do you explain the urgency, but also the potential?
The potential is huge, right? So also the challenge is also huge, and that is why the potential is huge. It's a blue ocean out there. Per year we have an emission rate of 40 billion tons of CO2 equivalent in the world, so 40 billion tons. And the IPCC calculated that we have to remove 5 to 10 gigatons of CO2 every year by 2050. So the challenge is really big. We have a capacity of 25 tons now with our container. We will scale up fast. We will be at megaton level, so 1 million tons in 2030, and at gigaton level scale in 2045. And it's really scalable. It's a modular approach, and we can scale it up by repeating the modular size, right? And then we have a bigger plant. So the technology is really scalable.
Blue energy has two faces, chemical and kinetic. We've seen chemical methods, osmotic power, ion gradients, but then there's the brute, beautiful force of waves, tides, and currents. Kinetic energy is loud, moving, shaped by storms and moon phases. Along coasts or out in the open seas, turbines and wave converters are designed to translate motion into power. Some anchored near shore, others battened into floating platforms. These systems face enormous challenges: corrosion, marine growth, extreme loads, and unpredictable directionality. With scale comes complexity. No wonder the Dutch don't just pipe water in. They also engineer machinery that must live in chaos.
As predictable as the position of the moon, we can predict when there's high flows and low flows for tidal energy. And so that is all usable in areas where there's constrictions around estuaries or around islands. And for example, we're now here in Vlissingen at the site where Water2Energy has a demonstration project. And we're here now at high tide, and that means that there's high current going through the sluice gate behind us. The next step is to look more in front of the coast. Everywhere where we have oceans, we have waves coming to our coastlines, and if we can harness them with smart, innovative technologies, then we have a complementary form of energy. So all these forms, salinity gradient, tidal energy, wave energy, they have a different type of profile of production and can be very complementary to wind and solar.
We talked about coastline, but obviously there's a huge potential in terms of harnessing energy for offshore plants as well.
As a small country with a relatively small sea, we have to be very space conscious. At the moment we have quite ambitious plans for developing offshore wind farms, and they're going to be co-located with other uses at sea. Of course there's existing oil and gas platforms, but slowly we are transitioning to green molecules and green electrons. And so we'll see large-scale electricity production at sea and also large-scale hydrogen production at sea.
Chemical approaches are powerful, but kinetic ones offer their own promise. Water2Energy is one company chasing kinetic. Vertical axis turbines placed in currents and tidal flows, often integrated with existing water infrastructure, like locks, gates, and canals. Their founder, Rainer Rischke, showed me one of their systems, turning a steady current into steady power. Not a boom boom of energy, but rather a pulse. Hidden, quiet, and scalable, and mind you, very Dutch in its practicality.
Actually, a vertical axis turbine has a vertical shaft, that's
Okay.
where the name comes from, and it has blades, and the blades are in the shape like an arrowing. And due to the water current, these blades start rotating. And independently from the direction, it always rotates in the same direction.
Okay.
The one you that see here is a model that we prepared for the port of Antwerp in Belgium. But here we have one without the yellow big part, of course a central shaft, but with 3 wings.
When you look at sort of tidal power in general, I think it's fair to say that it is a more reliable, perhaps more consistent type of renewable energy when it compared to solar or wind.
You're right.
How does that sort of fit into the renewable portfolio of the Netherlands?
I think it should fit in, but these days the Netherlands, they concentrate more on wind and solar. But imagine in wintertime, when our skies are dark in wintertime, grey. If you have a day without wind, there is no renewable energy from wind or solar.
Yeah.
The Germans have a very nice word for it. They call it dunkelflaute. It means dark and smooth.
Okay.
And then you have no sustainable energy anymore.
Yeah.
But this is predictable. Every day, 2 times we have a high tide, 2 times we have a low tide, and we can use the turbine in that direction, as you see now, but also in the other direction. So, in fact, only when the tide inside and outside is equal, there is no current. That's half an hour each time you have no energy generation. But the rest of the day, we can. So it's really predictable and it's always there.
But turbines turning vertically aren't the only story. Waves push sideways, surge, roll, and crash. That's a horizontal story. Kinetic power in motion. This is where WECO comes in. Their motto? Turning waves into watts. They've built a wave energy converter that captures lateral motion. Belts, floats, anchors, and generators all synchronized to harvest energy from horizontal wave forces. We'll be talking to Cas Vandervoort, one of the co-founders of WECO, who believes wave energy may be messy and wild, but also its untamed potential.
Yeah, so basically it's a floating platform with a screen underwater, and water particles push this screen towards the direction that the wave is traveling. And because wave particles are an orbital motion, actually at some point the water particles will go back and they will also retract the system to its neutral position. And because we have this system anchored to our main axis, as the system is moving, this axle is turning and driving the generator.
Right now you're just testing sort of like the motion of it, not sort of the internal energy generating part.
Yeah, so we actually use computer models and prototypes to validate the behavior of the system before we start building it and testing it at sea. And although computer models nowadays, they're very good, it's always nice to be able to physically see and see the behavior and have your prototype at hand. And we try all different iterations, changing dimensions, changing weight distributions, changing buoyancy distributions, to really see what is the effect of all these parameters.
Does bigger waves mean higher energy output?
Yeah, so that's an interesting thing. In general, if there's a higher wave, there's a higher potential of energy output. We're trying to learn the mechanism of our system so that we can tweak it according to the wave conditions that are at the different locations. For example, some clients, they want a more stable energy output, so be able to generate power at lower waves, but they don't mind curtailing at higher waves.
As a wave passes through water, it sets water particles into orbital motion. The Kaizamweg captures this orbital motion using a platform with floaters. When a wave moves past, one belt unrolls while the other one winds up. This creates torque on the shaft. Because of this design, the shaft keeps rotating in both directions of the wave. The rotating shaft drives a generator, turning wave motion into electricity. The electricity travels by cable to the shore, where it powers homes, businesses, and communities.
We basically designed it for a wave state, a sea state. So a sea state is actually a statistical measure of what kind of waves there will be at a certain hour, for example. So there can be high waves or smaller ones, and they're all together in a spectral density.
If you're going to stay true to the name and always pursuing improvement, in future models, what areas do you feel that you could actually stay true to your name?
So what we want to do is we make a building block. So that is the Kaizen. And we want to keep improving the building block, making it more efficient, making it cheaper, just to drive the cost of electricity down. And our vision is that it works together in a field, in a farm of hundreds of them working together. And if we can keep improving the building block, you can keep improving the whole farm.
And is there an AI factor to all this?
Yeah, so the Kaizen concept also goes for the control system, and we see that we can get a lot of benefit by making the system move better with the waves. So in our future versions, we want to have it learn basically continuously improving itself. So again, Kaizen, also with the control strategy, and well, we want to use AI for that.
The ocean is vast, powerful, and relentless. For millennia, it's fed us, moved ships and shaped climates. Now, it's showing up as one of our greatest sources of renewable energy. After sunlight, water is the world's most abundant resource. Chemical gradients, tidal pulses, and waves are all potential sources of electricity. Some technologies are mature, some are experimental, but each contributes to diversifying our energy future. Here in the Netherlands, the water has always threatened, but now it's becoming part of the solution.
From the same waters that once threatened the Dutch coast, a new wave of opportunity is rising. Several companies are proving that the ocean isn't just a challenge to manage, it is a force to harness. By turning the tides, waves, and offshore innovation into clean and renewable energy, they're helping write a new chapter in sustainable power. The Netherlands has always lived with water, fought it, shaped it, and mastered it. Now, with blue energy on the rise, that mastery is fueling a cleaner, smarter future. Well, that's it for this edition of NexTech. I'm Alijan Ayanlar, and we'll see you next time.